Hello and welcome everyone. I'm Edoardo Rossi, and in this presentation I'm going to show you our work on two advanced drilling technologies to improve the economics of deep geo-resources. So let's start from the background of this research. So looking at here the primary energy demand variation in the next 20 years, we can see here data from the International Energy Agency and how in some developing areas and also due to the increased world population, there will be an important increase here in yellow circles of the energy demanded in the next 20 years. Also, a current concern is about climate warming. So CO2 emissions here, we can see the 2°C scenario from IPCC. And therefore, if we want to follow this 2°C scenario, we need to decrease our CO2 emissions in the atmosphere and go towards a zero value by 2100. Therefore, if we want to combine and couple these two issues, we understand that we need to find a solution that can increase our future energy supply and at the same time also ensure the environmental sustainability. And therefore, many countries around the world are proposing and applying energy transition strategies looking at producing this increased energy generation using renewable energy sources. And so looking at conventional renewable energy sources such as wind, hydropower, and solar energy, we know here that there is a huge problem regarding their location and temporal dependency. So we cannot produce from these energy sources from all around the world. And also they show a short to long-term temporal dependency. On the other hand, deep geothermal energy, which means to use the huge amount of heat which is stored in the underground of our planet and use this to produce electricity, this could provide an interesting solution to increase our future energy supply and at the same time also being environmentally friendly. So one of the most interesting systems using deep geothermal energy is enhanced geothermal systems, so EGS. So this system wants to use the heat which is found at depths larger than 3 kilometers and generally low permeability basement rocks such as granite, and then circulating a fluid through an hydraulically stimulated or fractured network, extract this heat and at the surface produce electricity and or heat. Therefore, these systems show no location dependency. So as soon as we can construct these wells, these deep wells, we can have these systems everywhere in the world, and also there is no temporal dependency. So this system can provide baseload and dispatchable power, so on-demand power. However, one of the main challenges of deep geothermal energy is that we need to drill these wells very deeply, so deeper than 3 kilometers, and they're generally found in crystalline basement rocks, such as granite rocks. And this is a huge problem for conventional state-of-the-art mechanical drilling methods because they show poor drilling performances in these rocks. In fact, if you look at the project cost for a deep geothermal energy project, we can see that the drilling costs account for at least 50% of the overall project costs. And here, looking at a simplified formulation for the drilling costs, we can see that two main parameters are here the time to drill and the time to trip. So time to drill is inversely proportional to the drilling speed, so the rate of penetration ROP. So the faster we can drill, the lower or the smaller will be the time to drill, and therefore we can decrease the drilling costs. At the same time, also the wearing of the bead, so the smaller the wearing and the lower will be the time to drip, and therefore the drilling cost will be decreased. Therefore, we understand that we need to find a solution, a drilling solution to that can provide us with faster penetration and lower wearing of the bead, and therefore we can improve the economical viability and so the economics of the geothermal energy. Therefore, many researchers and research groups around the world are trying to develop and propose new technologies to improve the drilling performances in deep hard rocks. And so at ETH Zurich, we are studying and investigating two advanced drilling technologies, which are combined thermomechanical drilling, so CTMD, and also another technology which is called plasma pads for geo drilling, so PPGD. So in the next slides, I'm going to present you these two technologies, and so the concepts and also the numerical and experimental results that we have. So let's start with combined thermomechanical drilling. So I'm going to show you the concept of this technology and also some results and performance parameters. So the concept of combined thermomechanical drilling, so this is a hybrid drilling technology because uses a thermal assistance, which is done by flame jetting the material. and these facilitate conventional rotary drilling process because the flame jet will induce high temperatures and high heating rates on the rock material here, and therefore causing cracks in the rock. And therefore, this weakened rock can be removed with reduced efforts by conventional drilling cutters. And therefore, we can envision a faster penetration in the rock and reduce drill bit wear. And as I mentioned before, this will therefore improve the economics of deep geo-resources. So after performing many experiments in the lab and also developing the prototype of CTMD technology, we also went in the field. So we performed a field test in collaboration with the Goethe-Zentrum Bochum. And here you can see the drilling rig where we applied our CTMD prototype drill bit. And then we performed experiments in a granite rock sample, which is buried here in the rock. So we want to also measure many parameters during the test, and therefore then evaluate the performances of this technology. So this is a drawing of our prototype. So the most important part here is the drill head at the bottom, where we have here in red the combustion chamber. The combustion chamber is used to generate the flame jet, which is then conveyed down to the hybrid bit phase. At the hybrid bit phase, we have the flame jet nozzles, where the flame jet comes out here, these 4 nozzles, and then this wall component will rotate, and therefore the conventional drill bits, which are these ones, will therefore remove the rock much more easily. And then we have also drilling fluids, so water, to transport the cuttings. So let's take a look at the results of this field test. So what we want to do here is to compare conventional drilling, so only mechanical drilling, with our technology. So what we do is just to switch on the flame and see what happens concerning the penetration in the rock. So here, when we turn on the flame, we can see here in red the curve for the penetration using our CTMD novel technology, and we can see how the penetration can be improved by a factor of 3 compared to conventional drilling. And here also the slope of this curve is representative for the drilling speed. And here from an infrared camera image, I'm just showing here the flame jet coming out from the drill bit before the test, and therefore then this component is lowered and the test is performed. Okay, so let's now sum up these results from the field test and calculate some performance parameters, so rate of penetration, ROP, and also a measure for the beat lifetime, so the wearing of the beat. So for the rate of penetration, we compare always, as before, conventional drilling, so state-of-the-art drilling, with our novel technology, CTMD. And from the field test, we found that we have an increase of penetration by a factor of almost 3. For the specific wears, which is inversely proportional to the beat lifetime, here we can compare as well conventional drilling with our technology, and we can see that we can therefore improve the beat lifetime by a factor of 2.5 when we switch on the flame. So thermally assisted drilling can perform much better in this hard granite rock. Okay, so let's now move to the other technology. So plasma pulse for geodrilling, PPGD. So this is a completely different technology. So I'm going to show you the concept behind it and also some first results. So the concept of PPGD, so this is based on having electric discharge within the rock here, which will therefore break the rock by tensile fractures. So these are electrodes which are placed on top of the rock surface. So there is no contact or no mechanical removal, and therefore it is also called a contactless approach. And this means that we have no tool wearing whatsoever. So the drilling tool will practically no wear, have no wear. And also it is an energy efficient process because we break the rock by tensile fracturing the rock, and which is much more efficient compared to compressive stresses. And therefore we can say that we have reduced drilling efforts due to the above mentioned factors. So we now show here some numerical modeling of Electro-Pulse drilling. So what we do here is we place a slab of rock between 2 electrodes, and we apply a potential between these 2 electrodes. So we want to study here the damage mechanism during PPGD. So what happens when we apply this potential in the rock, and therefore study also the influence of different parameters. So the numerical results are shown in this slide here. And as we can see, the high electrical conductivity are shown, conductivity values are shown for high porosity minerals, and this causes the so some preferential pathways for the electric current, as you can see here. And this is then also responsible for localized heating in the rock, as you can see here in the temperature field, and therefore thermal strains are induced. These thermal strains are localized, and also the damage here is formed, as you can see in this figure. And what we do here is also to compare to different materials. So granite, much coarser grain size distribution, and granodiorite, which is much finer. And so we can see here that the finer the grain size, and the better the fragmentation using PPGD, because of the more localization of the thermal strains. Okay, so after this, we want to use this numerical modeling, or this numerical model, to also study different reservoir conditions for PPGD. So also experiments have been carried out, and so this is the proof of concept of the PPGD drill bit model here in the lab, where different materials have been drilled using this technology, so schist, granite, and brick. And also a proof of feasibility of this PPGD technology has been carried out in Russia, and under realistic condition, a 15-meter borehole in granite has been drilled. So nowadays, the parameter optimization in the Swiss PPGD experimental facility is going on, where different rock types are being drilled, and also different conditions are being tested. And I can show you some preliminary results for, so with demineralized water for PPGD. And as you can see here, the ROP, so rate of penetration, so the drilling speed is about, or a little bit higher than 7 meters per hour, which is a very interesting value compared to a value of 1 to 4 for 1 to 4 meters per hour for conventional mechanical drilling in these granite rocks. And also the drilling energy is a measure for the efficiency of the process. Okay, so now let's sum up what I just showed you, and also to conclude on the two drilling methods. Okay, so for CTMD, this is a hybrid drilling technology, meaning that we are combining thermal assistance, so flame jets, to conventional rotary drilling. And so we can envision an easier implementation path, a facilitated implementation path, due to the synergies that we have also with conventional drilling. And therefore also we could profit from the established know-how in the drilling industry. So the technology can also develop further using the know-how which is already out there for the conventional drilling systems. And as I showed, also the drilling performances using CTMD are enhanced by a factor of 3 regarding the drilling speed, and the bead lifetime can be improved by a factor of 2.5. So for PPGD, so here we want to drill the rock by fast electric pulses inside the material, and from numerical modeling we could show the influence of different minerals and micropores. And as you can see here from this picture, also the fluid salinity has an important impact on the fragmentation, and here also the temperature field, which is much more important when the fluid salinity is higher in the rock. And so from experiments and field tests, we have seen an improved rate of penetration, so improved drilling speed in hard granite, and a value of more than 7 meters per hour. And this technology features practically so no wearing of the drilling tools, which is very interesting for hard rock drilling. So the next step here is to study the impact of reservoir conditions, so in situ pressure and formation temperature, on the PPGD technology. So this is the end of my presentation. I want to thank the funding agency and also the partners who contributed in this work. So thank you very much for watching.